So today we looked at Chapter 0, and Chapter 0 was really just a set of preliminaries in which really the main goal was for us to think about proof and how to communicate proof and how to structure a proof. So we had three different results that each are basic sort of number theory results, proven in some different ways. So the first two examples both asked to prove the same statement, that if I have two odd integers, x and y, and I multiply them together, that product is still odd. So in the first example, 0, 0, 1, we saw a direct proof of this. And it was a direct proof because we began by assuming the hypothesis. And the hypothesis in this statement is that x and y are odd integers. So we assumed that p was true. And then we did the legwork of trying to deduce the conclusion. The product x, y is odd. Call that q. And that's what we ended up proving at the end of it. So that was our direct proof for the day. We assume x and y are odd, and then we used that assumption to prove that their product was odd. One of the things that I thought worked really well about this argument was in how the x and y being odd were connected directly with the definition of what that meant. I kind of like this indenting that happens right here, because it's first making an assertion, let's let x be odd. And then underneath that is the consequence of that assumption, right, where we directly plug in the definition of what it means for an integer to be odd. So it was clear to me when I looked through this exactly how those definitions were being used to support the assumption that p was true. And then we did some nifty algebra and justified that therefore x, y is also odd. Moving forward from there, we saw the same theorem, the same result, proved in an indirect fashion. Although the issue that I ended up taking with this was that a lot of this argument that we see here reads to be identical to the argument that we did in 0, 0, 1. Because what did we do here? We, again, assumed that p was true, but then also we assumed that q was false. So this is not q, if you like, right? And then from there, we were able to deduce at the end of this proof that in fact q was true. So the contradiction, to the extent that it exists in this proof, is that we sort of justified that both not q and q were true. That was the nature of the attempted contradiction here. The issue that I had was just that this assumption wasn't directly used in the proof. So the fact that x, y was even wasn't really it wasn't called upon in the logic. If it had been used in some substantive way, this would be more of a structurally indirect proof. But again, the way that I like to think of it is, if we can erase that assumption and the rest of the proof remains the same, then it probably wasn't as indirect of a proof as we thought that it was. So a good exercise might be to look back at this and see if there is a way to use the assumption that x, y is even to arrive at a contradiction of some other way. And in our last example, we saw that the square root of 2, in other words, a number whose square is equal to 2, is necessarily not rational. It's necessarily an irrational number. And it was a proof by contradiction because we began by assuming that p was true. So p here is the assertion that x is a number whose square is equal to 2. So that was p. And we also assumed that q was false. Q is the statement that x is not a rational number. So if we're assuming that q is false, that's what happened right here. Assume that there exists a rational number x whose square is equal to 2. So the not q portion of this proof was used right there to give us a fraction, a divided by b, where a and b are integers, b being non-zero, that characterizes the number x. So we assumed that q was false and that p was true, and p is that x is a number whose square is equal to 2. So here's p being true. So we assume p was true, and q was false. And then we went along and had to find a third hypothesis, a third statement, which is necessarily both true and false. And that was this assertion right here. That in the fraction which represents x, the numerator and denominator, a and b, are relatively prime. So the fraction is in its lowest terms. I would say, actually, if there's one word that I would change in what's written here, I would say that that's not really an assumption, that that's something that is given to us from outside of the subject matter of our course. It's really a number theory result. So I might just change this sentence here to say, according to number theory, we can choose A and B so that the greatest common divisor of A and B is equal to 1. That's something of no small consequence, especially in this proof, because that's the statement that we're going to directly contradict, which is done through this nifty argument about evenness that comes along through the process. So we show that if x squared is in fact equal to 2, then the argument is made that that necessarily implies that a squared is an even number. But if a squared is even, then a is even. And what supplies that logic is actually exercise 001. It's actually the contrapositive of exercise 001. So by exercise 001, if a squared is even, then a is even. Thus, by definition, a is equal to 2k, and then from there we also deduce that b squared is even, and thus b is even, and therefore b is equal to 2l, with l being an integer. And the contradiction, I'm just going to add one more sentence in here. How do we know that this was a contradiction? If b is even and a is even, then what is the greatest common divisor of a and b? What do we know about it? What divisor do a and b necessarily have in common according to what's written up here? 2. And so the greatest common divisor of a and b has to be at least equal to 2, because we know that they have a 2 in common, because they're both even numbers. And so that's why we get a contradiction here. As on the one hand, the assertion R is that the greatest common divisor is equal to 1, but then we're able to deduce that the greatest common divisor, that same greatest common divisor, is also greater than or equal to 2, and hence not equal to 1. Right? And so we have arrived at a contradiction, which shows that it is not possible to have P true and Q false. Because if it were possible, then this statement R would be simultaneously true and false.